Swayam Prabha. Digital India. Educated India.
So, we have solved the problem of transverse oscillation of uniform beam. We derived the equation of motion valid for a general element, which is this, where U represents the lateral displacement, which is a function of both its location, that means x, and also the instant of time under consideration. However, for a normal mode oscillation, we know that the solution will have to be in the form of a product of a function of x representing the mode shape and a harmonic function of time sin omega t. And when we substitute this in this equation, we get an ordinary differential equation in x of this form, where beta 4 is this, and we know that the general solution of x will be of this form. That means 4 constants C1, C2, C3, C4. First 2 terms are hyperbolic solution and the second 2 terms represent a harmonic solution. We have progressed up to this. Now, to make further progress, we have to take up individual cases, and as we have found in the case of bars and shafts, the value of beta we can find out from the boundary condition. So, therefore, our next step will be to take up individual cases. First, we will take case of simply supported beam. So, a beam with simple support at both ends, the length of the beam is L, the flexural rigidity, which is the product of the 2 terms E and I that appears here, is called flexural rigidity, EI. The cross sectional area is A, and density of the material is rho. Now, we have to find out the natural frequencies and mode shapes if possible. So, the boundary conditions here we notice that 4 constants A, B, C, D or C1, C2, C3, C4, whatever way we write those, they require 4 conditions. So, therefore, on each end we will have 2 conditions. So, here we find that if we take a coordinate system like this, origin here, then the conditions at x is equal to 0. That means this end. Now, it is simply supported at both ends. What is the meaning of that? Meaning is that at the simple support, your displacement is 0 all the time. That means x will have to be 0 all the time. So, therefore, displacement is 0. And bending moment will be 0 because simply support cannot provide any bending moment. Now, if we remember or during the derivation of this, or bending moment was proportional to and V was proportional to proportional to so therefore now del PU del X square when you are doing, so we can write this as and this will be so if m has to be 0 at all instants, so this term will have to be 0. This means d2x dx square. This is the double derivative of x with respect to x, and similarly at x is equal to L, the same two conditions must be valid. So these are the four conditions which the expression has to satisfy. Now x is equal to C1 cosine hyperbolic beta x plus C2 sine hyperbolic beta x plus C3 cosine beta x plus C4 sine beta x. So if you differentiate once with respect to x, this will be C1 beta differentiating once more, we may require for other conditions the third derivative also. So let us do it here, though we will not require this for the present problem. Now if we apply the first condition, that is at x is equal to 0, capital X is 0. Now at x is equal to 0, this term vanishes, this becomes 1, this becomes 1. So C1 plus C3 was 0. Similarly, we find that at x is equal to 0, d2x dx square, that is this term is also 0. If we put 0, then obviously this term goes and this term also goes. This becomes 1, this becomes 1. So the third condition, that means this moment condition, is C1 minus C3 equal to 0 as beta is not equal. So when C1 plus C3 is 0, C1 minus C3 is 0, this obviously says that C1 equal to C3. So now let us put the condition at x is equal to L. At x is equal to L also x is equal to 0, capital. So remember now that C1 and C3 terms are gone, so only these two terms remain. So at x is equal to L, C2 sine hyperbolic beta L plus C4 sine beta L equal to 0. And again at x is equal to L, moment is 0, but anyway C1 and C3 are already gone. So what remains is beta square if we take common, C2 minus C4. This beta square which was common we have removed. Again we find that for a non-trivial solution, now C2 and C4 they cannot be all zeros, then there is no vibration at all. So for a non-trivial solution we find that if we take up this, so what we will get, if we add these two, we get 2 C2 sine hyperbolic beta L equal to 0. Now we know that sine hyperbolic beta L cannot be 0 because it is an exponential function. So therefore the only possible thing is that C2 equal to. If C2 equal to 0 and this has to be 0, and so C4 sine beta L equal to 0. So therefore we find the situation is like this: C1 equal to 0, C3 equal to 0, C2 equal to 0, but C4 cannot be equal to 0. So therefore the only possible solution will be sine beta L, or beta will be equal to, or beta L will be equal to some integer multiple of pi, so I pi. So say beta I, so beta I is equal to I pi by L, and this we know from here is the fourth root of this. So from this we can, if we know the beta I, here we get, now we know that omega I square is equal to, from that equation will be EI by rho A into beta to the power 4. So beta I to the power 4. So omega I will be beta I square square root of now beta I square is nothing but I square pi square L square so this is the expression which gives us the natural frequency of a simply supported beam in its lateral height. So when I is equal to 1, that is the fundamental frequency, that is equal to pi square, which will be something like 9 point something. Second frequency will be obviously 2 into pi square, 2 square into pi square, that means 4 times that, and so on. And we also can find out here, in this case it is possible that x is equal to nothing but, since C1 equal to C2 equal to C3 equal to 0, so x in the ith mode is nothing but C4 say sine beta I into or since beta I equal to this, C sine I pi x by L. So therefore, it is possible in this particular case to find out the mode shape in this closed form, and we can see it is nothing but sine functions, and the various modes we can plot. First mode is obviously this, second mode will be, third mode will be, and so on. So therefore, we find that for a beam simply supported at both ends, the natural frequencies are given by this. They are interesting to note that mode shapes are same as the kind of mode shape we had in case of longitudinal vibration of bar. You remember that, with both ends say fixed. So for, if you want to consider a few other cases, I will just, without going through this detailed solution, what we can do, so let us consider the second case, which is another very commonly found situation that we want to call cantilever. That means one end fixed and the other end free. The length of the beam is L, its flexural rigidity is EI, the cross sectional area is A, and density of the material of the beam is rho. So now, in this particular case, the boundary condition at x equal to 0, displacement is 0 at all times, so x is equal to 0. Another thing what happens here, that whatever way it may go, its slope will have to be 0. Since it is rigidly connected here, so dx, the slope of the beam here will have to be 0 at all times. That means dx, will be 0. At x equal to L, that is a free end. Free end means what? There is neither any force acting on it nor any moment acting on it. So, since there is no moment acting on it, d2x dx square is 0, as we have seen in the previous case. And since there is no shear force acting, shear force is proportional to third derivative, if you remember. So these are the four boundary conditions in the case of a cantilever. When we use that, so like say these two, if we apply, So obviously at x is equal to 0, this term will vanish, this will be 1. So C1 plus C3 equal to 0. Next we go to the second condition, that is here. So now this term and this term goes. So it is C2 beta C2 plus beta C4. So C2 plus C4 equal to 0. So this will give C3 is equal to minus C1, and this will tell us C4 equal to minus C. Then we can use these in the two other equations and put x is equal to L and equate them to 0. So we will get these two equations then. Now, of course, we know that for a non-trivial solution for C1 and C2, the determinant of the coefficients must be 0, or determinant of the coefficients of C1 and C2 will be 0, which is this into this minus this into this that determinant must be equal to 0. So if we expand, cosine hyperbolic square beta L minus sine hyperbolic square beta L is equal to 1, then cosine square beta L plus sine square beta L will be another 1. What will be left with? 2. Or so this transcendental equation, its solution will give values of beta for case of cantilever beam. So this has to be solved numerically or looking into standard tables. I will give you the first three values. So beta 1 L is equal to 1.876, beta 2 L equal to 4.733, and beta 3L equal to 7.855, and when you go above beta 3, then there is a relationship beta IL is approximately equal to I minus half pi, or I equal to 4 pi 3. So once we know the betas, omega I is always like this. So here if we find the first root we are going to get will be approximately 3 point something divided by L square and this. So that is the natural frequency of a cantilever beam of length L, the second mode and so on. Only thing here we find that it is not possible to express the natural mode of oscillation in a closed form as it was possible in that case, because we don't have this kind of a closed form. It is only a numerical solution has led to the values of betas, and therefore we don't have an expression for beta, and that's why it is not possible to express the natural mode in closed form as it was possible in the case of simply supported. So same way, if we take a case where when we have a case 3, both ends fixed, for both ends fixed, our equation will be it was -1, now we have +1, and beta 1 L is equal to 1.8, sorry, 4.733, beta 2L is 7.855, beta 3L was 11, and beta IL equal to I plus half into 5 for I greater than 3. So from this we can find out the frequencies. We can take another case. One end fixed, other end simply separated. That is this is the situation. Here our equation is tan beta L equal to tan hyperbolic beta L. And for this, the solutions are beta 1 L equal to also you can find out. Let us solve a particular case. Example. So the example we take is 1n 6. And the other end elastically supported. So this stiffness is K of the spring, modulus, the rigidity modulus is EI for this beam, cross-sectional area is A, density of the material is rho, and length of the beam is L. So what will be the natural frequency? Now here the boundary condition will be what? At because we have to always start from the boundary conditions, so the general solution is in that form. Now here we find that at x is equal to 0, obviously we have taken the same kind of coordinate system as we have been doing always. At x is equal to 0, the deflection is 0 and slope also is 0. So at x equal to 0, x is 0 and dx. At x is equal to L, this is interesting and tricky. What we find that bending moment is 0, and bending moment is proportional to the second derivative, we have seen, and the force is not 0, but suppose if it has deflected by an amount x, then what will be the force? It will be k into x. So our equation for shear force was EI into d cube x by dx cube, that was the shear force. So therefore, d cube x dx cube will be shear force by EI. Now shear force or the force here will be whatever has the deflection, seeing stiffness into that deflection will be the force, and that divided by EI will be the third derivative. So these are the boundary conditions. When you solve, first of all, these two, if we substitute one thing at x is equal to 0, these two terms vanish, so C1 plus C3 equal to 0. Then again here at x is equal to 0, these two terms vanish. Beta into C2 minus plus beta into C4 is 0, beta goes, so therefore C2 plus C4 is also equal to 0. So therefore, just like previous case, we can express C3 as minus C1, C4 as minus C2, and then d2x dx square and d3x dx cube can be then expressed in terms of only C1 and C2. If we do that, we will get somewhat complicated equation. So if we now use the third condition, that means here at x is equal to L, this is equal to 0. Therefore, that gives us C1 cosine hyperbolic beta L plus beta L minus beta square term gets pulled out. So till this third condition there is no difficulty. We can always use these two to eliminate C3 and C4. The last condition is that when we use this for at x is equal to L, what we get? We get C1 this is equal to the value of x at small x is equal to L into k divided by EI and that beta cube which we take from common this side. So it will be k by beta cube EI and the value of x at x is equal to L. So it will be C1 So we can replace C2 by minus C1, C3 by minus C1 and C4 by minus C2. So we will get two equations with two unknowns, C1 and C2, and obviously we will finally get for non-trivial solution for non-trivial solution to exist, this condition has to be satisfied. So, for this problem, this is our equation or frequency equation, whatever we may say. This has to be solved numerically, obviously, when all the values are given and values of betas can be found out, infinite number of betas like beta 1, beta 2 and so on. So, in this case you can see it is no simple matter, it is only possible to solve numerically. We can check some limiting cases. So for example, if we find that the spring stiffness, for example, is 0. If the spring stiffness is 0, it means what? That this end is free. That means it is nothing but a cantilever beam. So this must go to cantilever beam. So you can see when k is 0, this whole goes and cosine beta L into cosine hyperbolic beta L must be equal to minus 1. That is the condition for cantilever beam we have already seen. So on the other hand, if k is infinite, it means what? That this end is simply supported. So it should match the case where one end is fixed, the other end is simply supported. If k is extremely large, then obviously this part is the large part and this can be ignored. So when k is infinitely large, this part goes out and so this part will have to be 0. Now this can be 0 only if this condition is satisfied. So sine beta L cosine hyperbolic beta L must be equal to cosine beta L sine hyperbolic beta L, or tan beta L equal to tan hyperbolic beta L. That you can see is the case where one end is fixed, one end is simply supported. So you can see the limiting cases are being satisfied, but otherwise solution will be possible only when the k is given and all other numerical quantities are prescribed. I think therefore this tells us that the method of solving problems which are subjected to transverse vibration. Now we have seen that the solution in closed form in the analytical way is possible only in case of very simple situations. But unfortunately in our real life engineering there will be many cases where the members or the elements, they do not satisfy the simplistic situation, or they do not satisfy the conditions of uniformity and all such things. Therefore in such cases the solution we can get either by numerical method, and nowadays with computer we can employ finite element technique, or otherwise when the designer of the machine is interested only in the fundamental frequency and also only an approximate estimate within plus minus few % of error, then the problem can be solved in an approximate method. And therefore now we will take up those kinds of techniques which will give us approximate values of the natural frequency in cases of more complicated geometric situations, like the beam is not uniform and cases are complicated. We have already seen, or we have already got some introduction to the approximate method when we were solving lump parameter system, and the similar techniques will be developed for continuous bodies also. The approximate method what we have discussed in the case of lump parameter system can be extended to continuous bodies also, because continuous bodies can be considered to be lump parameter systems with infinite degrees of freedom. So one of the most prominent method which we have discussed then we will apply here by slightly modifying that method suitable for continuous body, and there we come to our Rayleigh approach. We have seen that in Rayleigh's approach for solving free vibration problems without any damping, we took the condition, that means we considered the condition that in normal mode oscillation all the particles reach their maximum velocity situation or zero velocity situation simultaneously. That means the total energy is in the form of a potential energy when all the particles are with zero velocity. Similarly, when all the particles simultaneously attain the maximum speed, then the whole energy of the system, mechanical energy of the system, is in the form of kinetic energy. And since there is no dissipation or no change, so the maximum kinetic energy, which is equal to the total energy, must be equal to the maximum potential energy, which is also equal to the total energy. So therefore, our approach had been kinetic energy of the system maximum value is equal to potential energy of the system at maximum. And to find out this kinetic energy and potential energy, we assume the shape of deformation or deflection. And it has been shown earlier that even if this assumed form is not matching the exact one, or even if it has large error from a large deviation, the answer for the natural frequency will be reasonably period. That means the natural frequency which we find out from this is reasonably insensitive to the errors in the assumption of the deformation shape. So if an elastic body, its mode shape is say x, then what happens since it is the deformation. So the velocity of a particle is so therefore the kinetic energy is half if the element is of length dx, then its mass will be a into rho into dx, and maximum velocity will be omega x, and so therefore square of that. This has to be summed up for all the elements. That means we integrate for the whole bar or beam or shaft, whatever it may be. Of course, since it is linear deformation we are taking, we should take either beam or bars. Similarly, now say Umax. What is the expression for Umax? Say for the case of a bar. In the case of a bar, which is having longitudinal oscillation, then at a distance x, if you consider an element of length dx, and if the cross-sectional area is say a, which need not be constant, which may be a function of x, but at this distance, therefore, at this location, the element which is this is subjected to forces which is in this direction, and in this direction it is F plus dA. So you know that if we take an elastic body and stretch it by applying a force, so what will be the work done? Will be half into force into its elongation. How much is the elongation? Elongation is nothing but its strain into its length. Length of the element is dx. So if the strain here be epsilon and the length of the element be dx, then this is the amount of strain. So that into Fd. So again we know that F is equal to A into sigma, where sigma is the stress into area. So this is A into stress is equal to, we know that stress by strain is equal to E. So stress is equal to E into strain. So work done or the energy, whatever you may say, this work done is nothing but the energy stored in the object in the form of strain energy. It is nothing but half A E into epsilon square dx. Now the strain we have already derived is nothing but maximum strain is this. So, for the element, the energy stored is in that form. So, for the whole beam or bar rather, so this is for bar, longitudinal oscillation, not for beam. So, there now what we find that omega being same for all the elements, omegas can be approximately written as, from the T max is equal to U max condition, we can write that omega square equal to U max by A, E, rho, everything, they can be all functions of x. So, this is valid exactly, but in reality what happens, approximate method when we are talking about, this x is not known. So, what we do, we assume some mode shape. If we assume mode shape, then and substitute it there, we get reasonably accurate values of omega. Only thing, it is better to satisfy as many conditions on x as actually it has to satisfy on x. So, therefore, this should satisfy as possible. If you can satisfy all the boundary conditions, you will get best possible result. So, for example, if we take the simplest possible case to see the beauty of the method, let us take a case of a bar with one end fixed, other end free, whose solution we already know. And let us consider Xa, in very simple form, is say some constant into x. So, only thing what we satisfy, only condition, there are two conditions, that this is the fixed end, that means there is no displacement at x is equal to 0, and this is the free, that means strain is 0, that means dx is 0. Now, here we find that at x is equal to 0, Xa is 0, satisfying the condition. But the other end we are not satisfying the condition, dx is constant c and it is not equal to 0 at x is equal to L. So, we are satisfying only one of the two boundary conditions. But if you try to figure out the natural frequency, let us find out the fundamental frequency. So, first the numerator, which is a uniform case. So, A into E will go outside and dx will be simply c, so c square into dx. So, that numerator becomes A E c square L. The denominator, again A and rho both are uniform as a special case. So, this is equal to A rho c square So it is A rho C square L cube by 3. So using this we will get omega square approximately equal to this by this. So what we get? P E by L square rho. Or omega is approximately equal to 1.67 something, I don't know, L square root of E by rho. If you look into the exact value what we found, we have solved it already, is equal to pi by 2L square root of E by rho, which is equal to 3.14, it should be 51.5. So you see, it is reasonably close. The difference is only 0.1, maybe just 10%, not even 10%, less than that. With such a crude approximation, satisfying only one boundary condition. If we make it slightly better so that the slope here is 0, that is strain is 0 and the value is 0, which is not very difficult to get, then we will get very accurate results, which we will see in the subsequent discussion. So you can see that even a very crude approximation about the x, we get a reasonably rough estimate about the natural frequency, which in many cases may be enough so far as design is concerned.